Welcome to the Explainer. Consider this your ultimate survival guide for navigating both the physical universe and, of course, the Cambridge O-Level Physics 5054 exam. I am seriously thrilled to be walking you through this material today. You know, you can almost think of this as opening up a master mechanic's toolbox, but instead of pulling out wrenches and screwdrivers, we're going to be looking at the fundamental concepts you absolutely need to measure, quantify, and ultimately understand the world around you.
Okay, so here is exactly what we're going to conquer today to build out your toolkit. The physics roadmap, meet the physical quantities, scalars versus vectors, measuring irregular volumes, the crown mystery, and finally, we'll wrap up with the limits of time. Let's dive in.
Section 1. The Physics Roadmap, your 5054 battle plan. Before we master the physics, we really need to demystify the exam itself.
And this breakdown brilliantly illustrates the exam weighting. We're essentially looking at three distinct slices here. You've got paper 1, your multiple choice, making up 30%. Then paper 4, the alternative to practical, sitting at 20%. But wow, look at that massive 50% slice for paper 2, the theory paper. I mean, this shows exactly why focusing so heavily on paper 2's short answer and structured questions is absolutely crucial. It literally accounts for half your total grade. Developing a deep structural understanding of these foundational topics is exactly where you're going to win the most points.
Section 2. Meet the physical quantities, the foundational rules. Now that we know the stakes, we need to learn the basic rules of the game.
So a physical quantity is, simply put, something that is measurable. Actually, if you can't measure it, well, you can't really do physics with it. These three pillars right here represent our absolute basics: length measured in meters, mass in kilograms, and time in seconds. It's pretty wild to think about, but every single complex equation you're going to encounter later in physics ultimately traces its roots right back to these three simple, measurable units.
Section 3. Scalars versus vectors. Adding direction. Let's see how this toolkit starts to build out when we categorize these quantities based on whether direction actually matters.
Okay, so the crucial point here is comparing scalar quantities against vector quantities. Look at that list on the left. Scalar quantities are just amounts. It's what we call magnitude. We're talking things like mass, temperature, and energy. Like, if it's 20 degrees outside, it's just 20 degrees, right? It doesn't have a direction. But now look over at the right side. Vector quantities, things like force, velocity, and weight, they absolutely must include both an amount and a specific direction. I mean, think about it. If you apply a force of 10 newtons to a heavy box, you kind of need to know which way you're pushing it for that information to be at all useful. Section 4. Measuring irregular volumes, the displacement method. So we all know how to measure a straight, flat line with a ruler, but how in the world do you measure something that isn't perfectly straight, like the volume of some oddly shaped rock, where rulers are just completely useless?
Well, we use a pretty clever real-world life hack called measuring volume by displacement. It is remarkably simple and involves just 3 quick steps. Step 1, you partially fill a measuring cylinder with water and carefully note that exact starting volume. Step 2, you immerse the object completely into the water. And step 3, you just record the new volume. The increase in the water's volume exactly equals the object's volume.
What's really fascinating here is seeing the visual proof of those steps in action. Just treat it kind of like a classic interrogation. The irregular rock is our suspect, the measuring cylinder is the interrogation room, and that displaced water level rising, well, that gives us the immediate confession of its true volume. The water is simply pushed out of the way, perfectly mimicking the exact space the rock takes up.
Section 5. The crown mystery. Putting the tools to the test. Let's put our newly built toolkit to the ultimate test in a classic detective story. We've got 3 royal crowns and a suspected fraud.
All right, take a really close look at the data we have here. We have 3 crowns, A, B, and C. They all weigh exactly 3,750 grams. But by using our trusty water displacement method, we can see they have vastly different volumes. Crown A is 357 cubic centimeters, Crown B is 194, and Crown C is 315. Now, knowing that the density of real gold is 19.3 grams per cubic centimeter, that gives us a massive clue.
So, take a second and ask yourself, based purely on this data, which crown is the genuine, solid gold artifact? Just remember, density is simply mass divided by volume. The math completely gives it away. Since density equals mass divided by volume, calculating Crown B, so 3,750 grams divided by 194 cubic centimeters, gives us exactly 19.3, exposing crown B as the real gold. If you do the same math for the others, it exposes crown A as silver and crown C as a sneaky counterfeit mixture. This right here proves exactly why mastering these physical measurements is so incredibly powerful.
Section 6. The limits of time, beyond human perception. We're going to round out our toolkit with the measurement of time using stop clocks and digital timers. Because honestly, even the absolute best tools have limitations when human beings get involved.
We have these highly precise digital stopwatches today that can measure down to tiny fractions of a second. But we run into a major irony when trying to time something super simple, like a single oscillation of a pendulum swinging back and forth, just like the one we're looking at here.
As this quote right from our source material plainly states, a single period is usually too short time to measure accurately. See, the stopwatch is perfectly accurate, but human reaction time totally ruins the data. The tiny split-second delay it takes for your brain to tell your finger to click the button creates a massive margin of error for a single fast swing, which is exactly why physicists must determine average values for short intervals by measuring multiples. You times, say, 20 swings and divide the total by 20, rather than relying on a single isolated event.
And that brings this explainer to a pretty fascinating close. I mean, think about it. If a single swing of a basic pendulum is just too fast for our raw senses to capture without clever tricks and averages, what other physical realities are slipping right past our everyday perception? What else is just waiting for the right tools and the right mindset to uncover them? Keep that sense of curiosity sharp as you continue to build out your physics toolkit. Thanks so much for joining me on this explainer, and remember to keep questioning the universe around you.